Lesson 7 is a culturally important integral. So the first time I saw this integral, the professor who taught me how to evaluate this called it a culturally important integral. I think it's taken probably 10 years, but now I fully agree with him. So hopefully, if it doesn't seem all that culturally important to you, after a few years of experience, it'll improve a bit. So I'm going to look at a function called the standard normal density. This is the little phi that's been showing up in the Black-Scholes pricing formula. And it's defined to be 1 over the square root of 2 pi e to the minus x squared over 2. And we also, so little phi is not actually in the Black-Scholes pricing formula. It's this capital phi that's in the Black-Scholes pricing formula. I guess this showed up in the homework when we were looking at the derivatives of the Black-Scholes pricing formula. The capital phi is defined as the integral from minus infinity up to x of little phi of t dt. And so when I saw this the first time, a few questions immediately popped into mind. So I called this 2.5. So where does the 1 over the square root of 2 pi come from? It just seems sort of like a strange thing to stick in front of a function here. 2, why not use a closed form expression for this capital phi? And so it turns out this is a function that somebody actually proved does not have, so this function here, someone has proved this does not have an antiderivative. So there is no way to write down a closed form expression for this function capital phi. By closed form, I just mean something, like 1 minus the square root of something else that gives you the value of this capital phi function. If you wanted to write down a function, you would have to just keep writing and writing. You would need an infinite number of terms in order to write it down. And so then the 2.5 question was, where does this 1 over 2 pi come from? Because the whole reason it's here is that I want this to be a probability density function. So the part of one of the conditions, but there are two conditions. It has to be greater than 0, greater than or equal to 0 for all real numbers. So this satisfies that. It's actually greater than 0 for all real numbers. And it has to integrate to 1 when I integrate it from minus infinity to infinity. And so the reason this 1 over the square root of 2 pi is here is because this function here integrates to the square root of 2 pi. So if I wanted to integrate to 1, I need to divide by 1 over the square root of 2 pi. So those will cancel each other out. And when I do this integral, I'll have 1. But, yeah?
I have a weird question, but if we don't have a closed form expression for big phi, how do we know when we integrate it from negative infinity to infinity that it's equal to 1? So
well, the big phi doesn't have that property. The little one does. And so that's actually what this whole lesson will be about. So kind of in particular, I need to know exactly what you just asked. If I knew the capital phi, if I could write down that function and just take the limit as it goes to negative infinity and the limit as it goes to positive infinity, then I would be able to evaluate the area under that curve. And I would be able to tell you, I'd be able to tell you what it is. I'd be able to tell you that's the square root of 2 pi. Then I would say, well, if that is the square root of 2 pi, if I divide by the square root of 2 pi, it'll make it equal to 1. And so the rest of this lesson is to find out where this square root of 2 pi comes from. So since phi is a probability density function, the integral of phi over the real line, so I don't know why I put it twice here, but it still integrates to 1 even if you do it twice. And this implies that e to the minus x squared over 2 dx has to equal the square root of 2 pi. And you can make a change of variables to just have a slightly simpler version of the function without the x squared minus x squared divided by 2, just to have e to the minus x squared. And so this is actually what I'm going to try and show, that the integral of e to the minus x squared from minus infinity to infinity is equal to the square root of pi. And like I said before, if e to the minus x squared over 2 doesn't have an antiderivative, then this isn't going to either, because I was able to get this with just a simple change of, just a simple substitution. So this is actually going to use a trick very similar to what we used in the very first lesson when I was trying to come up with the value of an annuity. I'm going to pretend like I know what the answer is and say that it's equal to the value of this definite integral on the right-hand side. And then I'm going to mess around with this m as well as the integral. So I want to show that m is equal to the square root of 2 pi. And I could also write m as an integral from minus infinity to infinity of e to the minus y squared dy. So it doesn't matter what I call my variable. The value of this integral is going to be the same. So I'm going to have m defined in terms of x and m defined in terms of y. But they're going to be the same number. And now what I'd like to do is show that m squared is equal to pi. So if I can show that m squared is equal to pi, then that's the same thing as showing that m is equal to the square root of pi. And if you recall the separable integral lesson, so this now looks like what I would want to get from a function that's separable. But I can use that result backwards as well. So I'm going to start out by just trying to unseparate this and see what happens. So this is the double integral of a separable function. And I'll start unseparating the integral. So there's m squared again. And then I'll take the, let's see. So I've taken the y integral and kind of plucked it into here, which I can do because it's a constant. And then I'll get rid of my brackets. And now notice that e to the minus x squared, that's also a constant with respect to this integral on the right-hand side. And it looks like my dx disappeared from this line, but it showed up again here, so everything's okay. And so what I'm going to end up with is e to the minus x squared times e to the minus y squared. And by the properties of an exponential function, I can write that as e to the minus quantity x squared plus y squared. And then when you see x squared plus y squared, that's usually a pretty good hint that this might be something that would be simplified by switching to polar coordinates. So let's see what happens when I try and switch this into polar coordinates. So all I have to do to switch to polar coordinates, I replace the x by r cosine theta and the y by r sine theta. And then my dx dy becomes r dr d theta. So the r was the Jacobian. If I use the same transformation, if I use the same change of variables over and over and over again, the Jacobian's always going to be the same. So for the change to polar coordinates, the dy dx or dx dy is always going to become r dr d theta. So now I can write my m squared as the integral from 0 to 2 pi, integral from 0 to infinity of, well, this guy's going to get easier in just a second. So all I've done here is I've factored out the r squared, the negative r squared. And what's left inside these square brackets here is cosine squared theta plus sine squared theta. This is equal to 1. So I have e to the minus r squared. And then luckily, this little r that showed up thanks to the Jacobian is exactly what I need to be able to do a substitution to be able to integrate e to the minus r squared. And again, this is separable, so I can also take advantage of the fact that there's no theta in this part of the function. So I can move the integral with respect to theta out in front. And then I have minus 1/2 that I'm going to introduce here just so I can introduce a minus 2 here. So the minus 2 will cancel out the minus 1/2. If I make the substitution u equals minus r squared, then du is going to be minus 2 rdr. So I've made this, put this in brackets here. So I have e to the u after I make my u substitution. This bit in the parentheses is going to be du. And then if u is equal to minus r squared, the limits on u, they're going to start at 0, because negative 0 squared is still 0. And it will go to u equals negative infinity. The first integral is trivial, so that just becomes theta evaluated at 2 pi, so this will just be 2 pi. This is e to the u du, so that's a special function that it's its own derivative. So I end up with minus 1/2 e to the u evaluated at minus infinity and at 0. And so I have to be a little bit careful here. I can't just plug infinity in. But what I end up having is minus 1/2. So e to the, I'm going to replace u with t. So this is just e to the u evaluated at t, and then take the limit as t goes to minus infinity. And then I have to subtract the lower endpoint. So that's just going to be e to the u with u equals 0 substituted in. That'll be e to the 0, and anything to the 0 power is equal to 1. Or anything not 0 to the 0 power is equal to 1. So then I have minus 1/2 times this. The limit of e to the t as t goes to negative infinity, it gets smaller and smaller. So in the limit, that's just going to be 0. So I end up with 0 minus 1, so negative 1, times negative 1/2, and that gives me a half. This first bit is 2 pi, so 1/2 times 2 pi gives me pi. And I've been writing all of these equal signs here, so the whole long string of equalities is showing me that m squared is eventually equal to pi, and this is the thing that I set out to prove in the first place. So in summary, I started out with m equal to this integral that I couldn't find an antiderivative of. So it was difficult to evaluate. I was able to show that m squared was equal to pi. So m is equal to the square root of pi. And that gives us the result that we wanted, that this integral from minus infinity to infinity of e to the minus x squared dx is equal to the square root of pi.